Insufficient service entrance grounding in production plants can create a multitude of hazards and problems. These issues span electrical, mechanical, safety, and operational domains, and can even raise environmental concerns. From an electrical standpoint, insufficient grounding dramatically increases the potential for electrical shock. This is because it provides a high resistance path for fault currents, resulting in higher voltage levels on equipment and surfaces. Grounding is essential for protecting against overvoltage surges by providing a low resistance path for transient currents. Without proper grounding, overvoltages can occur, damaging equipment and increasing the risk of insulation breakdown. Poor grounding also creates high impedance paths for ground currents, which can generate electromagnetic interference, or EMI. This interference can disrupt control systems, communications, and other electronic equipment within the production plant. Mechanically, high resistance ground paths can cause arcing and overheating of electrical components. This can lead to fires or explosions, posing significant risk. Overvoltage and EMI can directly damage equipment, reducing its lifespan and negatively impacting productivity. Moreover, insufficient grounding accelerates corrosion of metal components, weakening their integrity and increasing the risk of failure. Safety is paramount in any production plant, and insufficient grounding presents several critical safety hazards. Electrical fires caused by insufficient grounding can be catastrophic, damaging property and endangering lives. Electrical shock and arc faults can cause serious injuries or even death to workers. Furthermore, insufficient grounding is a direct violation of electrical codes, which are in place to ensure safety and compliance. Operationally, the consequences of insufficient grounding can be severe. Overvoltage conditions and EMI can cause equipment malfunction or failure, leading to productivity losses and costly downtime. EMI caused by insufficient grounding can interfere with communication and control systems, significantly affecting plant operations. Equipment damage and corrosion resulting from insufficient grounding invariably lead to increased maintenance costs. Environmentally, the impacts of insufficient grounding are also noteworthy. Overvoltage conditions can cause insulation breakdown, potentially releasing hazardous gases into the environment. Arc faults and fires can release toxic gases and contaminants into the atmosphere, contributing to pollution. In summary, the hazards and problems associated with insufficient service entrance grounding in production plants are extensive and far-reaching. Addressing these issues through proper grounding practices is crucial for ensuring electrical safety, protecting equipment, maintaining operational efficiency, and minimizing environmental impact. Consider electrical shock. When the service entrance grounding is insufficient, the path of least resistance for fault currents is compromised. This means that in the event of a fault, such as a short circuit, the current may find an alternative path to ground, potentially through a person who comes into contact with the faulty equipment. The high resistance in the grounding system impedes the flow of fault current, causing the voltage on the equipment enclosure to rise to dangerous levels. This increased voltage creates a significant risk of electrical shock, which can range from a mild tingle to severe burns, cardiac arrest, or even death, depending on the magnitude and duration of the current flow. The effectiveness of grounding depends on the impedance of the grounding path. Ideally, the grounding path should have very low impedance to facilitate the immediate and safe dissipation of fault currents. When the impedance is high due to insufficient grounding, the protective devices, such as circuit breakers and fuses, may not operate quickly enough to clear the fault. This prolonged exposure to fault current increases the likelihood of electrical shock and equipment damage. Moreover, insufficient grounding can create a phenomenon known as touch potential, where a person can receive a shock by touching a grounded object that is not properly bonded to the grounding system. This can occur when the grounding conductor is undersized or when connections are loose or corroded. Therefore, adequate service entrance grounding is essential to minimize the risk of electrical shock by providing a low impedance path for fault currents, ensuring the prompt operation of protective devices, and preventing the development of dangerous touch potentials. Now consider overvoltage conditions. Grounding helps protect against overvoltage surges by providing a low resistance path for transient currents. Insufficient grounding can lead to overvoltages, damaging equipment and increasing the risk of insulation breakdown. Overvoltage conditions can arise from various sources, including lightning strikes, switching surges, and electrostatic discharge. Lightning strikes can introduce extremely high voltage surges into the electrical system, potentially exceeding the insulation rating of electrical equipment. Switching surges, which occur when electrical equipment is switched on or off, can also generate transient overvoltages. Electrostatic discharge caused by the buildup of static electricity can result in high-voltage sparks that can damage sensitive electronic components. When this service entrance grounding is inadequate, the electrical system becomes more vulnerable to these overvoltage events. The grounding system is designed to divert these transient currents to ground, preventing them from reaching and damaging sensitive equipment. However, when the grounding impedance is high, the transient currents are not effectively dissipated, leading to a buildup of voltage that could exceed the equipment's insulation rating. This can result in insulation breakdown, which can lead to equipment failure, fire hazards, and even explosions. Overvoltage conditions can also cause premature aging of electrical equipment. Repeated exposure to overvoltages can gradually degrade the insulation material, reducing its ability to withstand normal operating voltages. This can lead to unexpected equipment failures and increased maintenance costs. Therefore, proper service entrance grounding is crucial for mitigating the risk of overvoltage conditions by providing a low impedance path for transient currents, protecting electrical equipment from insulation breakdown and premature aging. Let's examine electromagnetic interference, or EMI. Poor grounding creates high impedance paths for ground currents, which can generate interference in control systems, communications, and other electronic equipment. Electromagnetic interference is the disturbance caused by electromagnetic radiation emitted from electrical and electronic devices. This interference can disrupt the proper functioning of other equipment, leading to malfunctions, data loss, and inaccurate readings. EMI can be classified into two main types: firstly, conducted EMI, and secondly, radiated EMI. Conducted EMI occurs when interference is transmitted through the electrical wiring, while radiated EMI occurs when interference is transmitted through the air. Grounding plays a critical role in minimizing both types of EMI. A well-designed grounding system provides a low impedance path for ground currents, preventing them from circulating through the electrical system and generating electromagnetic radiation. When the service entrance grounding is insufficient, the ground currents are forced to find alternative paths, often through equipment enclosures, cable shields, and other metallic structures. These alternative paths can have high impedance, leading to the generation of significant EMI. The EMI can interfere with sensitive electronic equipment, such as control systems, communication devices, and data processing equipment. This can result in erratic behavior, inaccurate readings, and even complete system failures. In industrial environments, EMI can disrupt the operation of critical processes, leading to production losses and safety hazards. Therefore, adequate service entrance grounding is essential to minimize EMI by providing a low impedance path for ground currents, preventing them from circulating through the electrical system and interfering with sensitive electronic equipment. Now let's consider arc faults. High resistance ground paths can cause arcing and overheating of electrical components, leading to fires or explosions. Arc faults are dangerous electrical events that occur when current flows through an unintended path due to insulation breakdown or loose connections. These faults can generate intense heat and light, creating a significant fire hazard. Arc faults can occur in various parts of the electrical system, including wiring, connectors, and equipment enclosures. When the service entrance grounding is insufficient, the high impedance ground path can exacerbate the effects of arc faults. The high impedance limits the flow of fault current, preventing the protective devices from quickly clearing the fault. This prolonged exposure to arc fault current can cause the surrounding materials to ignite, leading to a fire or explosion. Arc faults can also damage electrical equipment, causing insulation breakdown and premature failure. The intense heat generated by the arc can melt conductors, damage insulation, and weaken mechanical components. In industrial environments, arc faults can disrupt critical processes, leading to production losses, equipment downtime, and safety hazards. Therefore, proper service entrance grounding is crucial for mitigating the risk of arc faults by providing a low impedance path for fault currents, ensuring the prompt operation of protective devices, and preventing the ignition of surrounding materials. Now let's look at equipment damage. Overvoltage and EMI can damage equipment, reducing its lifespan and productivity. Electrical equipment is designed to operate within specific voltage and current limits. When these limits are exceeded, the equipment can be damaged or destroyed. Overvoltage conditions, as discussed earlier, can cause insulation breakdown, leading to equipment failure. EMI can also damage equipment by interfering with its internal circuitry. The electromagnetic radiation can induce unwanted currents and voltages in the electronic components, causing them to malfunction or overheat. This can lead to premature aging of the equipment and reduced lifespan. Damaged equipment can result in production losses, increased maintenance costs, and safety hazards. In industrial environments, equipment downtime can be extremely costly as it can disrupt critical processes and delay production schedules. Therefore, adequate service entrance grounding is essential to protect equipment from overvoltage and EMI by providing a low impedance path for transient current and preventing the generation of electromagnetic radiation. Now let's consider corrosion. Insufficient grounding accelerates corrosion of metal components, weakening their integrity and increasing the risk of failure. Corrosion is the gradual degradation of metal materials due to chemical reactions with their environment. This process can weaken the structural integrity of metal components, leading to failure and safety hazards. Corrosion can be accelerated by several factors, including moisture, temperature, and the presence of corrosive substances. Insufficient grounding can also contribute to corrosion by creating electrochemical reactions between different metal components. When the service entrance grounding is inadequate, stray currents can flow through the grounding system, creating a potential difference between different metal parts. This potential difference can drive the corrosion process, causing one metal to corrode more rapidly than another. The corrosion can weaken the metal components, reducing their ability to withstand mechanical stresses and increasing the risk of failure. In industrial environments, corrosion can affect critical equipment, such as pipes, tanks, and structural supports. This can lead to leaks, spills, and structural collapses, posing significant safety and environmental hazards. Therefore, proper service entrance grounding is crucial for minimizing corrosion by providing a low impedance path for stray currents, preventing electrochemical reactions between different metal components. Now let's look at the fire hazard. Electrical fires caused by insufficient grounding can be catastrophic, damaging property and endangering lives. Electrical fires are a significant safety hazard in industrial environments. These fires can be caused by various factors, including short circuits, overloads, and arc faults. Insufficient grounding can exacerbate the risk of electrical fires by creating high impedance paths for fault currents. When a fault occurs, the high impedance limits the flow of fault current, preventing the protective devices from quickly clearing the fault. This prolonged exposure to fault current can cause the surrounding materials to ignite, leading to a fire. Electrical fires can spread rapidly, consuming combustible materials and generating toxic smoke. These fires can cause extensive damage to property, disrupt critical processes, and endanger the lives of workers. Therefore, adequate service entrance grounding is essential to minimize the risk of electrical fires by providing a low impedance path for fault currents, ensuring the prompt operation of protective devices, and preventing the ignition of surrounding materials. Now let's consider employee safety. Electrical shock and arc faults can cause serious injuries or death to workers. Employee safety is of paramount importance in any industrial environment. Electrical hazards, such as electrical shock and arc faults, pose a significant risk to workers who come into contact with electrical equipment. Electrical shock can occur when a person touches a live conductor or a metal part that is not properly grounded. The severity of the shock depends on the magnitude and duration of the current flow. Electrical shock can cause muscle contractions, burns, cardiac arrest, and even death. Arc faults, as discussed earlier, can generate intense heat and light, causing severe burns to workers who are nearby. The intense heat can also ignite clothing and other combustible materials, leading to further injuries. Insufficient grounding can increase the risk of electrical shock and arc faults by creating high impedance paths for fault currents. This can prevent the protective devices from quickly clearing the fault, exposing workers to dangerous electrical hazards. Therefore, proper service entrance grounding is crucial for protecting employee safety by providing a low impedance path for fault currents, ensuring the prompt operation of protective devices, and preventing the occurrence of electrical shock and arc faults. Now let's look at code violations. Insufficient grounding is a violation of electrical codes, which are in place to ensure safety and compliance. Electrical codes, such as the National Electrical Code, or NEC, are a set of standards that govern the safe installation and maintenance of electrical systems. These codes are designed to protect people and property from electrical hazards. Insufficient grounding is a common violation of electrical codes. The NEC specifies the minimum requirements for grounding electrical systems, including the size of grounding conductors, the methods of grounding electrodes, and the bonding of metal parts. Failure to comply with these requirements can result in fines, penalties, and legal liabilities. In addition, code violations can increase the risk of electrical hazards, such as electrical shock, arc faults, and fires. Therefore, it is essential to ensure that electrical systems are properly grounded in accordance with the applicable electrical codes. Now let's consider power outages. Overvoltage conditions and EMI can cause equipment malfunction or failure, leading to productivity losses and downtime. Power outages can be costly and disruptive events for industrial facilities. These outages can be caused by various factors, including equipment failures, weather events, and grid disturbances. Overvoltage conditions and EMI, as discussed earlier, can contribute to power outages by causing equipment malfunctions and failures. When electrical equipment is damaged by overvoltage or EMI, it may need to be repaired or replaced, resulting in downtime and production losses. Power outages can also disrupt critical processes, leading to further delays and financial losses. Therefore, adequate service entrance grounding is essential to minimize the risk of power outages by protecting equipment from overvoltage and EMI. Now let's consider communication and control disruptions. EMI caused by insufficient grounding can interfere with communication and control systems, affecting plant operations. Communication and control systems are essential for the efficient and reliable operation of industrial facilities. These systems are used to monitor and control various processes, such as manufacturing, production, and distribution. EMI can interfere with the operation of communication and control systems by disrupting the signals transmitted between devices. This can lead to inaccurate readings, faulty commands, and even complete system failures. In industrial environments, communication and control disruptions can have serious consequences, such as production losses, equipment damage, and safety hazards. Therefore, adequate service entrance grounding is essential to minimize EMI and ensure the reliable operation of communication and control systems. Now let's consider increased maintenance costs. Equipment damage and corrosion due to insufficient grounding can result in higher maintenance costs. Maintenance costs are a significant expense for industrial facilities. These costs include the labor, materials, and equipment required to keep the facility's equipment and systems in good working order. Insufficient grounding can increase maintenance costs by causing equipment damage and corrosion. Damaged equipment requires more frequent repairs and replacement, while corrosion can weaken metal components, leading to premature failure. These factors can significantly increase the overall maintenance costs for the facility. Therefore, proper service entrance grounding is crucial for minimizing maintenance costs by protecting equipment from damage and corrosion. Now let's consider insulation breakdown. Overvoltage conditions can cause insulation breakdown, releasing hazardous gases into the environment. Insulation breakdown occurs when the insulation material surrounding electrical conductors is damaged or deteriorated, allowing current to flow through unintended paths. This can lead to short circuits, ground faults, and other electrical hazards. Overvoltage conditions, as discussed earlier, can cause insulation breakdown by exceeding the insulation rating of the material. When the insulation breaks down, it can release hazardous gases into the environment. These gases can be toxic or flammable, posing a risk to human health and safety. In addition, insulation breakdown can damage electrical equipment, leading to further hazards. Therefore, adequate service entrance grounding is essential to prevent insulation breakdown and protect the environment. Now let's consider pollution. Arc faults and fires can release toxic gases and contaminants into the atmosphere. Arc faults and fires, as discussed earlier, can generate intense heat and light, causing damage to electrical equipment and surrounding materials. These events can also release toxic gases and contaminants into the atmosphere. The gases and contaminants can include carbon monoxide, sulfur dioxide, and other harmful substances. These pollutants can have a negative impact on air quality, human health, and the environment. In addition, arc faults and fires can release particulate matter into the atmosphere, contributing to smog and other forms of pollution. Therefore, adequate service entrance grounding is essential to prevent arc faults and fires and protect the environment from pollution. Proper grounding techniques are imperative for safety and operational reliability. Grounding refers to intentionally creating a low-impedance path from electrical equipment to the earth. This path allows fault currents to flow safely back to the source, tripping circuit breakers or fuses to quickly de-energize the circuit. This prevents dangerous voltage buildup on equipment enclosures, minimizing the risk of electrical shock. The NEC outlines specific requirements for grounding and bonding to ensure electrical safety. Section 250 covers grounding and bonding requirements, including the size of grounding conductors, the types of grounding electrodes permitted, and the methods of bonding metal parts. Understanding and adhering to these requirements is crucial for preventing electrical hazards. One common grounding electrode is a ground rod, typically made of copper or copper-clad steel. The NEC specifies the minimum size and length of ground rods, as well as the methods of installation. Ground rods must be driven into the earth to a sufficient depth to ensure good contact with the soil. Another common grounding electrode is a metal water pipe. The NEC allows the use of metal water pipes as grounding electrodes, provided that certain conditions are met. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be supplemented by another grounding electrode, such as a ground rod. The grounding electrode conductor, or GEC, connects the grounding electrode to the electrical system. The NEC specifies the minimum size of the GEC, based on the size of the service entrance conductors. The GEC must be installed in a manner that protects it from physical damage. Bonding refers to connecting all metal parts of the electrical system together to create a common ground. This includes equipment enclosures, metal conduits, and metal water pipes. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of electrical shock. The equipment grounding conductor, or EC, connects the metal parts of the electrical system to the grounding system. The NEC specifies the minimum size of the EGC, based on the size of the circuit conductors. The EGC must be installed in the same raceway or cable as the circuit conductors. Proper grounding and bonding are essential for electrical safety. These techniques provide a low impedance path for fault currents, minimizing the risk of electrical shock, arc faults, and fires. Adhering to the NEC requirements for grounding and bonding is crucial for ensuring the safety of electrical systems. Firstly, inspect grounding electrodes for corrosion and damage. Secondly, test grounding electrode resistance to ensure it meets code requirements. Thirdly, verify the integrity of grounding conductors and connections. Fourthly, confirm proper bonding of metal enclosures and equipment. Fifthly, use calibrated instruments for accurate measurements. Sixthly, document all inspection and testing results. Seventhly, provide training to personnel on grounding procedures. Eighthly, establish a regular maintenance schedule for grounding systems. Ninthly, promptly address any grounding deficiencies identified. Tenthly, consult with qualified electrical professionals for complex grounding issues.